Red lights on a slick pump as I miss the other day.
The oceans and the seas of the world cover almost 3/4 of the surface of the planet and are very important areas of sediment accumulation. The oceans are underlain by oceanic crust, but at their margins are areas of continental crust that may be flooded by seawater on occasion. These are known as continental shelves. The extent of marine flooding of these continental margins has varied over time due to plate movements and the rise and fall in global sea level related to climate changes. The sedimentary successions in these shallow shelf areas provide us with a record of global and local tectonic and climatic variations. There's considerable variety in the sedimentation that occurs in the marine realm, but there are a number of physical, chemical, and biological processes that are common to many of the marine environments. Physical processes include the formation of currents driven by winds, water density, temperature, and salinity variations, as well as tidal forces. Together, these have a strong effect on the transport and deposition of sediment in seas. Chemical reactions in seawater lead to the formation of new minerals and the modification of detrital sediment. Seas are also full of a wide variety of organisms that evolved in the marine realm long before terrestrial organisms and continue to occupy many habitats within the waters and on the sea floor. The remains of these organisms and the evidence for their existence together provide important clues in the understanding of paleoenvironments. The bathymetry, the shape and depth of the seafloor, is fundamentally determined by the plate tectonic processes that create ocean basins by seafloor spreading. The spreading ridges are areas of young, hot basaltic crust that is relatively buoyant and typically around 2,500 meters below sea level. Away from the ridges, the water depth increases as older crust cools and subsides, leaving most of the ocean floor between about 4,000 and 5,000 meters below sea level. The deepest parts of the oceans are the ocean trenches created by the subduction zones. This is where water depths can be more than 10,000 meters. At the ocean margins, the transition from ocean crust to continental crust underlies the continental rise and the continental slope, which are the lower and upper parts of the bathymetric profile from the deep ocean to the shelf. The angle of the continental slope is relatively steep, usually between about 2 and 7 degrees, whereas the continental rise is a lower angle slope down to the edge of the abyssal plain. The continental shelf itself is underlain by continental crust, and the junction between the shelf and the slope usually occurs at about 200 meters below sea level at present-day margins, known as the shelf edge break. Continental shelves are very gently sloping, with gradients ranging from steep shelves of 1 in 40 to more typical gradients of 1 in 1,000. These may extend for tens to hundreds of kilometers from the coastline to the shelf edge break. Large areas of continental crust that are covered with seawater, which are mainly bordered by land masses and connected by straits to the oceans, are called epicontinental seas, also known as epiric seas. The areas of epicontinental seas are greatest when relative sea levels are at their highest worldwide. A nomenclature for the division of the marine realm based on these depth zones is shown here. The shelf area down to 200-meter water depth is called the neritic zone. The bathyl zone corresponds to the continental slope and extends from 200 meters to 2,000 meters water depth, while the abyssal zone is the ocean floor below 2,000 meters. A depth limit to this zone can also be applied at about 5,000 meters, below which the deepest parts of the oceans are called the hadal zone. The shelf, or neritic environment, can be usefully further divided into depth-controlled zones, although in this case the divisions are not defined by absolute depths, but the depths to which certain processes operate. Their range therefore varies according to the conditions in a particular basin, because the depths to which tidal processes, waves, and storms affect the shelf will vary considerably. The foreshore is a region between the mean high water level and the mean low water marks of the tides. Depending on the tidal range, this may be a vertical distance of anything from a few tens of centimeters to many meters. The seaward extent of the foreshore is also governed by the slope, and it may be anywhere from a few meters if the shelf is steeply sloping and where the tidal range is small, to over a kilometer in places where there's a high tidal range and a gently sloping shelf. The foreshore is a part of the beach environment or littoral zone. The shore face is defined as the region of the shelf between the low tide mark and the depth to which waves normally affect the sea bottom. This is also known as the fair weather wave base. The lower depth the shore face reaches depends on the energy of the waves in the area, but is typically somewhere between 5 and 20 meters. The width of the shore face will be governed by the shelf slope as well as the depth of the fair weather wave base, and may be hundreds of meters to kilometers across. In deeper water, it is only the larger, higher energy waves generated by storms that affect the seabed. The depth to which this occurs is the storm wave base, and this is very variable on different shelves. In some places it may be as little as 20 meters water depth, but it can be from 50 to 200 meters water depth if the shelf borders an ocean with a large fetch for storm waves. This deeper shelf area between the fair weather and the storm wave bases is called the offshore transition zone. The offshore zone is the region below storm wave base and extends out to the shelf edge break at about 200 meters depth. The activities of a number of physical, chemical, and biological processes are determined by water depth, and these in turn influence the sediment accumulation on different parts of the sea floor. The tidal bulge created in the open ocean is only a few tens of centimeters, but of course the difference between high and low tide is many meters in some places, so there must be a mechanism to amplify the vertical change in sea level. The tidal bulge can be considered as a wave of water that passes over the surface of the earth. In any waveform, resonance effects are created by the shape of the boundaries of the vessel that the wave is moving through. In oceans and seas, the shape of the continental shelf as it shallows towards land, indentations of the coastline, and narrow straits between seas can all create resonance effects in the tidal wave. These can increase the amplitude of the tide, and locally the tidal range is increased to several meters by tidal resonance effects. The highest tidal ranges in the world today are in bays on continental shelves, such as the Bay of Fundy on the Atlantic seaboard of Canada, which has a tidal range of over 15 meters. There's currently some controversy with another small town on the east coast of Canada about having potentially a higher tidal range, but we'll see how that works out. In addition to the influence of land masses, the movement of water between high and low tide conditions is also affected by the Coriolis effect. Water masses moving in the northern hemisphere are deflected to the right of their path, and in the southern hemisphere to the left. These effects break up the tidal wave into a series of amphidromic cells, and at the center of each cell there's an amphidromic point around which the tidal wave rotates. At this point there's no change in the water level during the tidal cycle. All oceans are divided into a number of major amphidromic cells, and there are additional smaller cells in shelf areas such as in the North Sea and small seas such as the Gulf of Mexico. Tidal ranges are therefore very variable, and within a body of water the pattern of tides can be quite complex. In the North Sea, for example, the tidal range varies from less than a meter to over 6 meters. For sedimentological purposes, it is useful to divide tidal ranges into the following categories. Up to 2 meters mean tidal range is microtidal. Between 2 and 4 meters range is mesotidal, and over 4 meters range is macrotidal. The horizontal movement of water induced by tides is a tidal current. Tidal currents are weak in microtidal regimes, more pronounced if the range is mesotidal, and are capable of carrying large quantities of sediment in macrotidal regimes. Nearshore tidal currents show a number of features that produce recognizable characteristics in sediment deposited by them. First, tidal currents regularly change direction from flood tide current, which moves water onshore between the low and high tides, and the ebb tide current, which flows in the opposite direction as water levels return to low tide. These are bipolar currents acting in two opposite directions. Second, the tidal flow varies in velocity in a cyclical manner. At times of high and low tide, the water is still. But as the tide turns, the water starts to move and increases in velocity up to a peak at the mid-tide point in each direction. Third, the strength of the flow is directly related to the difference between the levels of the high and low tides. As the tidal range varies according to a series of cycles, the velocity of the current varies in the same pattern. The strongest tidal currents occur when there are the highest spring tides at the spring and autumn equinoxes. The rotational pattern of the tidal wave within amphidromic cells results in a flow of water that follows a circular or elliptical pattern. These rotary tides can be important currents on shelves and in epicontinental seas. During the course of the tidal cycle, the current varies in strength but does not change direction, and therefore there may be no period of slack water. These offshore tidal currents are important processes in the transport and deposition of sediment on some shelf areas. An analysis of current directions recorded by cross-bedding in sands deposited by tidal currents may show a bimodal, that is, two main directions of flow, and bipolar, that is, two opposite directions of flow pattern. It should be noted, however, that these opposing paleoflow directions are not seen in all tidal sediments. First, the flow in one direction, either the ebb or flood tide, may be much stronger than the other, and second, the two flows might be widely separated and only one may have been active in the area examined. Under favorable circumstances, bipolar cross-stratification may be seen in a single vertical section produced by alternating directions of migration of ripples or dunes. This is known as herringbone cross-stratification, and it results from a tidal current flowing predominantly in one direction for a period of time, probably many years, followed by a change in the pattern of tidal flow that results in another period of opposite flow. This pattern of alternating direction should not be interpreted as a diurnal pattern, as this would imply unrealistically high rates of sediment accumulation. The herringbone pattern is characteristic of tidal sedimentation, but is not found in all circumstances. At the time of high or low tide, when the current is changing direction, there's a short period when there's no flow. When the water is relatively still, some of the suspended load may be deposited as a thin layer of mud. When the current becomes stronger during the next tide, the mud layer is not necessarily removed because the clay-rich sediment may be cohesive, and this makes it resistant to erosion. Mud drapes formed in this way can be seen in wave and current ripple laminated sands deposited in shallow water in places such as tidal mudflats. Heterolithic beds formed in this way display flasiure or lenticular lamination depending on the proportion of sand and mud present. Mud drapes can also occur within crossbeds. A laminae of sand is deposited on the lee slope of the subaqueous dune during strong tidal flow, but as the tide changes direction, mud falls out of suspension and drapes the subaqueous dune. There are circumstances where mud drapes can form in other depositional regimes, for example in rivers that have only seasonal flow, but they are most common in tidal settings. Abundant regular mud drapes are a good indicator of a tidally influenced environment. In places where there is one dominant direction of tidal current, the bedforms migrate in that direction, producing unidirectional cross-stratification. These bedforms can be modified by the reverse current, principally by the removal of the crest of a subaqueous dune. When the bedform recommences migration in the direction of the dominant flow, the cross strata build out from the eroded surface. This leaves a minor erosion surface within the cross stratification that is termed a reactivation surface. The strength of the tidal current varies cyclically, and hence its capacity to carry sediment varies in the same way. At the highest tides, the current is strongest, enabling more transport and deposition of sand on the bedforms in the flow. When the difference between the high and low tide is smaller, the current will transport a reduced bed load, or there may be no sediment movement at all. A cyclical variation in the thickness of foreset laminae and crossbeds may therefore be attributed to variations in flow strength in the neap spring tide cycle, and these are called tidal bundles. In an idealized case, laminae would exhibit thickness variations in cycles of multiples of 7 or 14, but there's usually no sedimentation or bedform migration during weaker parts of the tidal cycle, so this ideal pattern is rarely seen.
Slip the night from a shame, make a marked card late.